Okay. Okay. So, yeah. Hi. Welcome to the week 2 of the problem solving session for the computational complexity course. And um, okay. So, okay. Before I um, begin the session, I just want to make an announcement that the next session will not happen on the upcoming Monday. So um, anyway, I'll talk about you later. What is a possible slot for rescheduling? Just okay. I mean, I'll talk about it at the end. And yeah, so the topics for today are the co-NP class, um, NP completeness. We had some discussion on this last time, and or just completeness in general. Okay, and the polynomial hierarchy. Okay, so what we saw last time, just to quickly recall, were two classes essentially, P and NP. So P is the set of is the class of languages that are that can be solved in by a deterministic Turing machine that runs in polynomial time. And we defined NP to be the class of languages that can be solved by non-deterministic Turing machines in polytime. Or equivalently, we had a definition with respect to verifier machine, which says that uh, yeah, it says that there is a verifier machine. There is an x for all x in the language. There is a y. Length of y is bounded by poly, and there is a verifier machine which accepts, and this verifier machine is a deterministic polytime machine. Okay, so these were the two equivalent definition. One is a verification based definition, and the other is a definition with respect uh, to the non-deterministic Turing machine. Okay, and then we saw that P is contained in NP. Okay, that is I mean, you can simply think of uh, yeah, think of y as something trivial, and the machine M that you had here. Okay, okay, yeah, and the machine M that you had here, think of it as the verifier V, and y is something trivial. So we are not even using this guess, we are just solving it even without looking at y. So therefore you can think of um, every language in P to be in NP. It's just a general a more general definition. So the the question that we had was whether P is equal to NP. We do not know, but in the quest to answering this, uh, what we came up with the first hard language for this class NP, which was CKTSAT. This was due to the Cook-Levin theorem. So Cook-Levin theorem shows that um, for all A in NP, A reduces to CKTSAT in polynomial time. So this is a polynomial time many one reduction. And we call such problems as NP hard. So this is an NP hard problem, and NP complete is the class of languages that are in NP and are NP hard. So this definition here says is the definition of hardness. Okay, and so therefore that shows that CKTSAT is the first NP complete language that we have. Okay, but um, but how do we draw this class, right? So can I draw it like this? If I draw it like this, that would mean that, I mean, we don't mean that this is separate from P. It's just it's just an illustrative demonstrative diagram which just represents the subset relation. We don't know whether NP complete and P intersect. If they do, then that would mean that if the intersection of um, okay, so if this class NP complete that we have has a non-trivial intersection with the class P, then what does that mean? Can you infer something?
Okay, so if the intersection of so what was the question? The intersection of NP complete and P class
Hmm. Is
is
non-empty.
not
Hmm.
is not is not phi. So
Hmm.
there is an overlapping of the NP complete and the P class.
Hmm.
So since NP complete is the representative problem of the NP class,
Hmm.
and probably this is the toughest problem in the NP class.
Hmm.
So if the intersection is not phi,
Hmm.
so this would refer that yes, I mean P is equally, I mean is equally hard. So that would refer to that as if the P is equal to NP. NP, I mean P is equal to NP.
In fact, yeah, in fact, P is equal to NP is equal to NP complete.
Yes. But then, can you? But then, is there any problem,
Mm-hmm.
and which is there in NP and which
Mm-hmm.
is not NP complete?
Which is there in NP, which is not NP complete. Okay, so yeah, so in fact, I guess some 60 years ago, there were the sorry. Okay. Hmm. Hmm. There's a problem called primes. Oh, what's happening? Hmm. Okay, called primes, which is that simply that I'll give you as input on an integer which is represented as binary. I'll give you an integer n, and you say yes if it is prime and no otherwise. Okay, so so is this problem uh, in NP?
Yes, because now we do have an algorithm which runs in the polynomial time, AKS algorithm, and which can solve this algorithm in the polynomial time. So since every P is there in the NP, so clearly this is there in NP.
Since what? Mm.
Since every P is there in NP, and this primes is the element of P, so therefore primes is the element of NP as well.
Right, yeah. But even if you don't know that, let's say you don't know that primes has a polytime algorithm and you want to show it's in NP using either of the two definitions, either the verification.
Yes, yes. We can go for the verification because if you give me a number, I can know, but then how to verify this thing in the polynomial time unless I know an algorithm which runs in the polynomial time. Because is prime, I mean, the AKS algorithm is for the solution of is prime problem only.
Hmm.
So unless we know that there exists an algorithm which runs in the polynomial time and wherein we can check the primeness of the number, even if you give me a number, even if you give me a certificate, then how would I verify whether this number indeed is a prime number or not? So I need
Hmm.
to have this prior information with me that I do have an algorithm which runs in the polynomial time and which will check the primeness of a number.
Hmm. Okay. So, um, actually, you can always, okay, once you know that there is a polynomial time algorithm, you can of course come up with a certificate using that algorithm and show that it is in NP that way, or just use the fact that P is contained in NP. But that is just one way of showing that it's in NP. Let's say we are not it's not the time today that we have this AKS algorithm and we know it's a polytime algorithm. Let's say we are in those times when we didn't know that a polytime algorithm existed, and I want to show that it's in NP. Then I'm saying that you don't really need the polytime algorithm to show that it's in NP. You can come up with certificate. It's not a trivial certificate. I agree with that. But you can come up with a certificate which is intuitive. I mean, it's intuitive to come up with, but it need not. I mean, it doesn't use the polytime algorithm, and that wouldn't solve. Okay, let's say. So primes is in, which is the natural. I mean, certificate. Sorry. Is it easy to show that it's in co-NP?
Uh, because this primes would be the element of co-NP. Because if a number, for all those numbers which are not prime, I can always. So a language is the element of co-NP if its complement is there in NP.
Hmm.
So the negation of the primes, would
Hmm.
it be the element of the complement of primes would be the element of NP as well? Um, I'm not sure.
Exactly. Huh.
I'm not
Exactly.
sure.
Hmm.
So how to show that the negation or the complement of primes is the element of NP then?
Oh no, that is not what we are showing. Okay, we're not showing that. So negation of this language is composite, right? So you will say yes if the number is composite, and
Right, right.
okay,
Yes. So this is the element of co-NP, and probably primes is there at the intersection of NP and then co-NP.
exactly, exactly. So you know that there's a trivial way to. I mean, there's a very easy way to show to come up with a certificate for composite, which is that you'll give me a factor and I'll verify whether the factor that you gave me divides n or not. And therefore, I have an easy certificate for this, right?
Yes.
Hmm. Therefore, it's natural for you to give a certificate for no instance of prime. So, if the answer is no, you can convince me easily. Therefore, primes is in co-NP, right?
Yes. It's
Okay.
clear. Yeah.
So, what we know right now, assuming we don't know a case, what we know is that primes is in co-NP. And what I'm saying is that there is a way to come up with a certificate, an NP, um, a verifier for the primes in the yes instance as well. It's not trivial, but at the same time, it's not okay. We'll not get into the details, but let's say I can show you that. So then that would just put primes in NP intersection co-NP. That does not solve the that's still not enough to conclude that primes has a polytime algorithm. That's not what we'll be able to say, even if I come up with an NP um, algorithm.
Uh, yes, because this P, whether P is equal to the intersection of NP and co-NP is still an open problem.
Yes, this is one big open problem. We don't know whether we know that P is contained in NP intersection co-NP, but we don't know whether this containment is strict.
Yes.
So this is an open problem. Okay, but yeah, so but you can think about this particular, this particular fact that how do you come up with an, even without using the AKS, how do you show that it's an NP? We'll not get into it right now, but yeah, so what I was trying to say, and to answer your question is, primes was one such candidate which we knew was an NP, but for a long time we didn't know whether it's, we couldn't show that it's NP complete, there was no reduction. At the same time, we couldn't show it's in P. But okay, I don't remember the year. I'm not sure, but yeah. So yeah,
It was in
Agrawal,
2002, I guess.
it was
I
in
mean, 2002, I guess.
2002,
Somewhere in
somewhere
2002
around.
plus minus 2, yeah.
Okay, so Agrawal, Kayal, and Saxena, they showed that primality testing can be done in polynomial time. So therefore, now this problem fits into the class of P. So okay, mm, okay, but there are several other candidates out here. One example is graph isomorphism. Uh, Another example, which is another problem which is very well studied, is minimum circuit size problem. So I'll just give the definitions of these. Um, yeah, there are several. There are many other problems. So in fact, if you just search, these are called NP intermediate problem, or simply NPI. So if you just search about this, you'll find a list of a lot of problems that uh, we don't know whether they are hard, and we can't even come up with a polytime algorithm. So um, yeah, so I'll just give you definitions of both of them. These are just two of them which are very well studied. So the graph isomorphism problem is that I have two graphs as input to me, G1 and G2, and assume for now these are undirected. And we're going to say yes if G1 is isomorphic to G2 and no other way. So what do we mean by isomorphic? So okay, I don't have a good example at the moment, but okay, so I'll just okay. I think I'll have to work backwards for coming up with an example, but okay. So what it essentially means is that there is some relabeling of these vertices. So let's say I want to relabel x5 with A with B. I'll okay. I'm sort of working backward right now because I don't have an example at hand, but okay.
Uh,
Mm-hmm.
Yes, but then I understood this thing that there exists a mapping such that whenever a vertex say V1 is element of the graph G1, then we have say the phi of V1 would definitely map to the vertex of the graph G2, and this would be a one-to-one, and I mean this would be a
Is
bijective
the
map.
bijection exactly?
Yes, yes,
So
yes.
essentially, there is a relabeling of the vertices, which preserves the adjacency matrix.
Yes, yes.
Okay, so why is this an NP? Quickly,
Yes, because if you give me a certificate,
mm-hmm.
then I can do some pre-processing over the certificate, like say a single vertex has not been counted. Some pre-processing can be done, and even if we do not do any pre-processing, then if you give me a certificate, then I can verify that whether uh, this certificate is I mean whichever certificate you have given me is isomorphic to the originally given graph or not. I can do this thing in the polynomial time.
Exactly. So the certificate would be, you just give me the function. So the certificate here would be that it's a function from, uh, let's say, V is the set of vertices here, or let's say V of G1 to V of G2. So it just tells you that okay, map x1 with A, think of x2 as B, and so on. So it's going to give me a relabeling essentially. And once I have that, I'm just going to check for every pair, xi xj. um, yeah, what we'll do is, so let's say phi is the function. I'll check if xi xj is an edge in g1 if and only if f of xi xj, f of xi and f of xj is an edge in g2. So checking this particular thing, checking whether it's an edge, is just a order one time operation. Even if it's a adjacency matrix, or it's given as a, okay, whatever be the representation, this is an order one, a constant time operation. Similarly, this is a constant time operation because the graphs are given to us. And how many such pairs are there?
So number of edges would be NC2 number of n choose 2 number of edges would be there.
Exactly.
If
So there are only roughly order n square or n choose too many such pairs, and each operation can be done in odd constant time. So this verification can be done in quadratic time. But coming up with a polytime algorithm for this is not, is not easy, or we don't know an algorithm as such. You can think of brute force algorithms that will, yeah, that will do exactly the kind of things that we did, go through all possible permutations. Then the kind of research that goes into this is assume that the GIs that are given to us are special in the sense you can think of these as trees. Let's say these are not general graphs. I just give you two trees, and I'm going to ask you whether the trees are isomorphic. Then can you come up with polytime algorithm? So the idea is that if you have a strategy for relaxed versions, can we use it, can we lift that strategy to get more and more general algorithms? So that is one side of research that goes into it. Okay. And are there any questions about this problem?
yes, so it's okay that the problem is in NP, but then how to show that this problem is not NP complete?
Showing that something is not NP complete would be even more uh, even more difficult, um, because all you know is how to show a reduction, uh, is to show hardness. Showing that there's no reduction is even harder. Or
So then how to show that this is an NP intermediate problem and this problem is not NP complete. So because we
uh,
took this problem to show that there are problems in the NP class and
hmm,
which are not NP complete.
hmm.
So in
So okay,
this,
okay.
yeah.
So we are not saying that this problem is not NP complete, right? We don't know whether it is NP complete. We don't know whether it is NP complete, and we don't know whether it is NP.
So it could be the case that probably we might not have found the right problem and which can be reduced into this problem. And quite possible one fine day we could find a problem and which has already been proved as NP complete and which can be reduced into this problem. So because
Which can be reduced
basically
into
yeah,
what problem?
uh, so reduced into this graph isomorphism problem so that
Okay,
this
okay,
problem also becomes element
okay.
of the
Right, right.
NPC. Yeah, because my query is that are there problems in the NP class and which are not NP complete, which have been proved that these problems are not NP complete. Graph isomorphism is an element of NP, but since we do not know whether it is NP complete or not, so either we make the statement that either all NP class problems are NP complete, or we do not know whether they are NP complete or not.
Okay, yeah. So if there is a problem that which is in NP, which we know is not NP complete, then that would have already solved the P versus NP problem. That would mean that P is not equal to NP.
Um,
Uh, okay, sorry, just a second. Let me think. Hmm. Okay. So we're just saying that there would be a hierarchy. So if okay, what we're saying is if there is a problem in NP which is not NP complete, then so okay. Hmm. Okay. If this is the case that this is strict, then that would mean that um, okay, I'm sort of okay. Just a sec. Okay, my claim is that this would imply that P is not equal to NP. Let me think about it. Okay, yeah. So that this is fine, right? I mean, this is okay. So if L is in L is in NP. Mm, okay.
Probably,
That would just mean that there are hierarchies here.
yes,
Hmm.
yes, yes. Probably there could be problems which could be tougher than the P class,
Hmm.
but then those problems are not at least as hard as a NP complete problem
Hmm.
is.
Hmm.
So yeah, so graph isomorphism certainly is not one such problem because
Mm-hmm.
we do not know for sure that whether this graph isomorphism is not an element of NPC.
Hmm.
One fine day, it could be proved as NPC. Is
Hmm.
it? Okay, okay, yes. But I have one more related question related to this stuff. So, are so similar to probably similar to this one that do we have problems which are NP hard and which are not so I mean, so which one is difficult? NP hard or so? So can you give? I mean, are there problems which are NP hard but not NP complete? And the thing is that those problems should not be the undecidable ones. So are there problems which are NP hard but not NP complete? Uh, I mean that are there problems
Yeah.
which are not the element
So,
of NP, but
hmm.
then all the NP can be reduced into that problem?
Yeah. So what you are asking is this is NP and this is the class of NP hard problems, and the intersection is what we called as NP complete. So you are asking whether this is non-empty.
Yes, yes, yes. So I'm looking for some problems which are in this region, which are not the element of NP, but then yes, those problems are NP,
Hmm.
and the
So
problem should not be the undecidable.
yeah, of course, whatever we are looking at is within the decidable world. All, I mean, everything that will define from now on will be in the decidable world. Okay. Okay, so from what I recall, yeah, I think there are languages here. I don't recall specifically at the moment, but I'll look into it and I'll maybe mail you if I have some information.
Yes,
Okay.
yes, 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 sure.
Um, yeah.
Yeah, because whenever I search, I mean this thing, so often the answers which I find in the online forums are that halting problem, but then that problem
It
is
is,
undecidable.
yeah.
Yeah, yes, yes, thanks.
Okay. I'll look into this part. Okay. So, okay, so maybe I'll define the other problem because that also connects to the polynomial hierarchy. So we were here, right? We defined the GI, the graph isomorphism. I'll define the minimum circuit size problem because, yeah, things will naturally take over from there. Okay, so this is the minimum. circuit size problem. Have you heard of this?
No, no, I'm not. Probably you last in the last session you gave some example of it wherein you want to, but that was something else.
Huh.
That was a reduction of the range of something, not related to
Right.
this.
Yeah, that was the range of it. Yeah. So the problem is that input to U is a circuit C, and the circuit C computes a function f, right? But I mean, if I give you a circuit C, it's computing some function over, say, um 0 1 to the n to 0 1, because the output is a boolean value. So it's computing some function f, and the point is that this may not be the minimum circuit computing the same function. I can, if I give you a function, you can come up with so many um, so many circuits corresponding to it. So for example, if I give you an arbitrary function c, can you come up with a cnf? uh, I give you the truth table. Can you come? How do you come up with a cnf for it?
Uh, so conjunctive normal form there used to be. Uh, uh, so first I need to bring everything into the clausal form, and then it should be the end of, or then it should be the CNF. So this should be uh, the end of the ors, I guess. Yeah.
Right. So from this truth table that you have, x1 to xn and all the way up to all ones, and this is the value, the output of function. So this may be, yeah, depends on the function, the output, what is the output based on, corresponding to that input. So if I give you this truth table, how will you come up with these clauses?
So these clauses, so the CNF would be the end of the clauses, right? And the clause would be all ORed. So I mean,
Yeah. So okay, so what we are saying is that this function will give 1 if any of the following clauses is a 1. And what does that correspond to? That corresponds to the ones of this truth table. So this is these correspond to the clauses, the ones whose output is a 1. And I want to say that if the input matches with these values, then my formula, then this particular clause should turn out to be 1. So how do we capture this? This will be, if it's a 0, then I'll write negation, x1 bar, x2 bar, and so on. And if it's a 1, then I'll write the same variable. So if I substitute this particular value 0 0, okay, I think I'm writing, sorry, I'm writing it the other way around. This is, it's a DNF thing that I'm writing, sorry. Okay, so what we're saying is the function will be 1 if any of these clauses is 1. So that means if the input matches with this, or wherever you have 1, or this and so on, then I should say, I should output a 1, otherwise I'll output a 0. So if the input is, let's say, all zeros and 1, then the falses, these will become true, and yeah, xn goes as true, so therefore this gives a true. So it's essentially the SOP and POS thing that you might have seen earlier. So the point I'm trying to say is that if I this is just one way of coming up with a circuit, the DNF, the or the CNF, and so on. And what is the size of this circuit? The size is the number of gates that are there. Okay, so in this case, what is an upper bound of the, if you, let's say, come up with a DNF, then what is an upper bound on the size of this DNF?
so upper bound would be that, like say, for this end thing, I would be requiring two variables. So then I keep on dividing it by 2, and then I would be having, say, if there are n number of the Boolean literals, so then the height would be log 2n. Log 2n. Within log 2n thing, I think I should be able to, because then
Okay,
I
what
need to
is?
pick, say, I need to make the pairs at the base.
Oh, sorry,
And
sorry. So this is okay. Sorry, I drew it like this, but this sort of looks like this. I mean, there are n. It's an AND of n variables. Sorry, this is an AND.
I see.
Okay, so the question is how many? What is the fan in of this top gate? Like how many such clauses may I need in the worst case? So this output gate is only one, but the second layer of the circuit, right? That is the fan in of this gate. How many of them can there be?
Oh, I see. So it shows that the inputs can be reused.
Inputs
Is
can be
this
reused. Yes,
real
yes.
right? So in the worst case, quite possible that we are using all n's input for this thing, and then so then I mean the finite would be in the worst case scenario would be equals to n. I would be requiring n number of the end circuits.
Okay. So what is the size of this? What is the size height of this truth table?
So truth table height would be 2 raised to the power n.
Right, 2 to the power n. And when do I draw an AND gate, an AND circuit here? Whenever I see a 1 in that table.
Okay, okay. So whenever I see one, okay, okay. So yes, so then 2 raised to the power n minus 1 I mean, would be the
Would be,
height,
yeah,
fan in
so
the quantity.
order 2 to the n. Even if half of
Yes,
them are ones, I'll need
yes,
2 to the n minus 1. I mean, 2 to the n minus 1.
yes.
So that means this could be exponential size circuit because input to me is, I mean, uh, yeah, let's say the circuit is, or okay, I'll not talk about the circuit directly. Let's say the function is on n variables. Even then, the circuit could be very large. The circuit uh, could be exponential sized. But I am interested in poly-sized circuits. So we don't know whether, I mean, we are not claiming that there is always a polynomial size circuit. That is a separate area of research. But ideally, I want a circuit which is as small as possible, corresponding to that function. So, yeah. So what the minimum circuit size problem says is that I'll give you a circuit. Okay. And it's given a circuit, it's definitely computing some function over n variables. Now, I want you to come up with some other circuit such that uh, C2, the function computed by C2 is the same as the function computed by C1, but C2 is the smallest circuit computing F. Is the problem clear?
Yes, so smallest would mean what? Small, the minimum number of the
Gates.
gates. Okay, okay, I
Yes.
see. Yeah.
Okay. So how do you show that this is in NP?
Because if you give me an assignment, if you give me a string, the values of x1 to xn, I can tell you that whether the output is 1 or not.
Sorry. What is the guess? The certificate that you gave me?
So certificate would be that if you give me an assignment of say x1 to xn,
Hmm.
uh, then I can tell you that because in that case the one of the clause will return a true value. So then if one of the clause returns a true value, then the entire value will came out to be true. Right? So if you give me the an assignment, I can check whether this result into a true value or not.
But when do I say that two circuits are computing the same function?
Oh, I see. Yes, so I did not pay enough attention to this output thing. Probably the problem formulation is not clear to me. So we have been given what, say, input, what these C1 and C2 are?
Huh. So C1 is a circuit that I'm giving to you, and C2, which is the output, is the smallest circuit that computes the same function that C1 computed.
Oh, I see. So to me, probably this is not only the element of NP, but this is undecidable problem, I guess, because if I correlate a circuitry by a program, then basically the indirect this question would be like, if you give me two programs, so can I tell you whether both the programs are same or not? Both the programs are doing the same functionality or not? And so this thing is undecidable. This thing is undecidable. We
Mm-hmm.
used to study Rice's theorem, and yeah, which says that the yeah something related to, like, say, any non-trivial property of a recursively unequilibrium language is undecidable kind of thing. So if we can correlate a circuitry as a program, then this problem is same as determining whether two programs are same or not. So
Okay,
uh,
but uh, but what I'm giving you is very specific, right? I mean, I'm not giving you any general program. Okay, I'm giving you a circuit which is basically a graph, right? So I can, I mean, I can think of this as a DAG, okay, and the
okay.
labeled gates and so on. So it's not any general program. I'm giving you very special, very restricted um, input. So maybe, I mean, so okay, in fact, in this case, it's possible to come up with a Turing machine that, given C1 and C2, checks whether they are same or not. So how will you, let's say, think of an algorithm. I give you two circuits, C1 and C2, and you want to check whether they are the same or not. What is a trivial, forget about the time also.
So, so trivial procedure would be that for every input, either both should generate the output as one or both should generate the output as zero, and I'll have brute force. I mean, I'll have to check 2 to the power n number of the possibilities.
Exactly. So what you'll do is you'll write a machine or an algorithm which for all x checks whether uh, c1 of x is same as c2 of x. So this can be done by a Turing machine, right?
Yes, yes.
Okay. So what we are saying is this part of the check can be done by a Turing machine. So this is okay. There may be, I mean, if we do it this way, then we are sort of going over all possibilities. But you may even be able to look at the structure of the circuits and say something about it. So this trivial way would take exponential amount of time. But let's say I'm able to do this check somehow. Even then, that's not the final answer. So any C2 which computes the same function is not the answer that we want. We want the smallest such C2 possible. uh,
Okay.
right. So how do you write this in terms of the quantifications? So you might have seen in the lectures the there exist for all thing.
Oh, so there exists a y
Hmm.
such that for all x,
Hmm.
which is an element of uh, say
Circuits,
and then
the
C1
class.
circuit C1, right? And that the output of the C2 and C1 is same. So there exists a y such that no. I mean this. I mean I do not require the two quantification here. So there exists probably the one thing would be sufficient. If I want to show that f of C2 is same as the f of C1, then I need that for all x, and which is the element of the assignments for all this thing x1 till xn. uh, so but then Yeah. So, but then where is the question of the certificate here? Because I'll have to check this thing for all the 2 raised to the power n number of the assignments. For all x, wherein every x is an element of is an assignment. So I'll have to check it for all possible x.
Hmm.
I mean, both C1 and C2 should return the same value.
Hmm.
Then only they are equal. Uh, so
Right.
there is
So,
so there is no question of existential one, I guess. I mean, to
right,
include
right,
that certificate thing, I need to have something which is of existential nature.
right. But you want to capture the fact that it's the smallest circuit.
Oh yes. So that thing is a certificate that I cannot do.
Hmm.
I mean, I cannot achieve this thing
Hmm.
by smaller than this thing C2. So there exists a y, but then that for all x, f of C2 is equal to f of C1. But how to write this thing mathematically that this y is the smallest one?
Hmm. So how do we write that this is the smallest one? What we're saying is that for all circuits C prime such that f of C prime is same as f of C. Um, okay, so I'll write it freshly. So what we're saying is that there exists a minimum size circuit C2 that I want, such that for all C prime, f of C prime is equal to f of C or C1, what I don't know what I called it. Yeah, f of such that this happens, it has to be that uh, the size of C prime is strictly greater than the size of C2, and also of course f of C2 is same as f of C1. So what we're saying is that if for every other circuit C prime which computes the same function that we wanted, it has to be the case that its size is more than the size of C2. That is, it is not the minimum size circuit computing.
Yes, yes.
So this sort of, I mean, okay. So in case of NP, the definition of NP, what you had was that there is a y. So x is in L if and only if there is a y such that v of xy accepts. So this condition is something that we can check in deterministic polynomial time. And this was the quantification that we had. Whereas in the case of co-NP, we had that x is in L if and only if for all y v of xy accepts. So yeah, so this corresponds to the NP quantification. This corresponds to our co-NP quantification, and this there exists for all is like a um, is like a next level of hierarchy to it. So we don't know provable. So okay, I'll first define this. So whenever you have quantification like this, that x is in L if and only if there exists y for all z, v of yz accepts, where this is a deterministic polytime machine, and of course y and z are also polysized. Okay, then we say that L is in sigma 2p. So when we say sigma 2p, we have this sort of a quantification there exists for all. So adding another level of, let's say in this case there was no need, but even if it is there exists there, okay, I'll write it here. There exists x1, there exists x2 for all y2, for all y, for all y2. Let's say it is like that. So does this mean, okay, before sorry, even before I jump there, is this part clear, the definition of the sigma 2p class?
Yes, yes, it is
Hmm.
clear.
Okay, so even if I had, let's say I'm extending it and I have something like this, um, then there is a verifier machine, x1, x2, y1, y2 accepts. Okay, and assume everything is polysized and so on, polytime, wherever needed. So is this any different from what we defined earlier? Is this definition any, I mean, would you put it up in the hierarchy or something with respect to?
So I can view this in two ways. So either I can view it like say there exists x1, there exists x2 as there exists x1 and x2 one thing, and then for all there exists a tuple say y1 comma y2. So effectively I would be having two quantifiers then. So then this would be sigma 2p as well. However, if I include a dummy universal quantifier after there exists x1, like say there exists x1 for all something z1,
Z.
and alternatively, so then I would be having 1 2 3 4, I would be having effectively eight number of the quantifiers, but then those z1 z2 z3 and z4 will become the part of this verifier as well. Probably that won't be appropriate, but this tuple part seems to be more appropriate. There exists x1 comma x2, such that for all y1 comma y2 this entire thing is true. So this is sigma 2p, I guess.
Exactly. So this also is sigma 2p because for the same reason that you mentioned. So this is also sigma 2p because I could just think of x1 x2 as a tuple or something. So I'll just say there exists x1 x2 and also this as y1 y2. But if there is some other quantifier here, then okay, let's say there is some other quantifier here z1, and let me add one more here, or maybe there exists z2. Then what is the um, what is the class in the polynomial hierarchy? Is this okay? Maybe I'll rewrite this if it's not readable. So we're saying there exists x1 for all z1, there exists x2 for all y1, there exists z2 for all y2. What is the class?
So now here I have one, two, three, four, five, six. Till now you have written only six quantifiers. So then this would be, and it's starting with an existential one. So therefore this is sigma 2 6.
Exactly. So this would be sigma 26. Sorry, sigma p6. And because it
Yes.
starts with a there exists. And if I started with for all and had this six many alternations, that would be, I would call it pi 26. Uh, Pi p6. And so np for us is nothing but sigma 1. And co np is nothing but pi 1. So there is,
Yes.
yes. So there is this hierarchy that we have here. Um, and yeah, you can think of intersections of um, yeah sigma 1 and pi 1, sigma 2 and pi 2. These are called delta 1, delta 2, and so on. This is nothing but our np intersection co np class, and p sits inside this. So, okay, we'll not get into this. So, this is the polynomial hierarchy that we have. The P here signifies all the constraints that we had, that all of these, uh, all of these are poly-sized, and the verified machine runs in polynomial time. So, what we know for, all we know for sure is that sigma 2p is contained in sigma 1p and so on. Okay, but we do not know whether the containments are strict. So whether this whether this is proper, none of that is known. And yeah,
Why and what could be the implication of having the strict containment?
um, well, then you would have collapsed uh, collapse this whole hierarchy to that level, right, where the containment happens. For example, this containment here would directly implies p not equals np.
It's okay, but then if this sigma 2p is the proper subset of,
Oh,
no. You wrote this thing correctly or in the reverse direction, this subset thing. Uh, you wrote
oh, sorry,
sigma
sorry,
2.
sorry. Sorry, I meant, yeah. Thanks, yeah. Yeah, thanks for pointing out. So I meant this way.
Yes, yes. So now say if the sigma 1p is the proper subset of is contained in sigma 2p.
Properly
So
contained in sigma 2.
yeah, yeah.
Okay.
So how does this relate to the collapse of the entire hierarchy then?
Okay. Huh. So then, okay, I think, okay, I'm not sure if this was done in the class, but okay. Um, okay, so let me talk about, let's say, sigma 3p. Mm, okay. And then I have there exist for all, there exist. Okay, I think it's easier to talk in terms of pi 3p, let's say. Okay, so I'll talk about pi 3p. This is for all, there exist for all. Okay,
Yes.
so now what I'm saying is that sigma 2p. Um, okay, sorry, did I say? Sorry. I think I meant the other way around. So if these were equal, so if sigma 2p were equal to sigma 1p,
Then hierarchy will
then the
collapse. It's
hierarchy
okay.
collapses. Yeah.
That is well understood because in that case one of the quantifier will become redundant, and if like
Exactly. Then you can replace this.
yes,
Yeah. So okay. Yeah. So the collapse happen in the equal. Yeah, in the equal case.
yes,
So if p were equal to np, then the whole thing would have collapsed to p.
right. And if it is the case of the containment, then I mean probably this could be an open problem. I mean, probably nobody might be knowing what is the right answer. That what if uh,
What is
there is,
the
there is
open? Sorry. What is the
uh,
open problem?
so I'm not sure, but then it is just my guess that if sigma 1p is strictly contained in sigma 2p, so then that would mean that this universal quantifier, I mean, is actually is very very strong because like say there exist is contained there in there exist and then universal one. So
Hmm.
this will show the power of the universal quantifier that actually means something.
Hmm.
So, so probably we do not know for sure that whether this one quantifier is so strong uh,
Hmm.
that we are having such a separate hierarchy kind of thing,
Hmm.
such very very rigid,
Hmm.
distinction.
Hmm.
I don't know. I don't know what is the correct. What is the real situation? Yeah.
Hmm. Yeah. And yeah, there are natural problems that fall into each of these classes. I mean, we've seen enough examples of NP, co-NP, and so on. So I mean, a lot of those properties hold. So if L is in sigma 2p, then its complement is in pi 2p, and so on. Same thing holds every. So a lot of properties that we saw with respect to p and p do hold in this hierarchy as well. And there are problems that you might have seen in the class that naturally fall into these classes. Or you can even come up with the um, sort of uh, representatives of those classes. So, for example, we have this notion of 3-SAT or click or vertex cover that we call among the hardest of the NP problems, right? So, similarly, you can come up with notions of hardest of this problem. So, you might have seen the quantified Boolean formula problem.
Yes, TQBF and TQBF was the P space complete problem. Yeah. Truly quantified Boolean formula, TQBF. Yeah.
Okay, so okay, we're just talking about like a um, natural extension of the SAT, for example. That I mean, you can think of um, yeah, you can think of, let's say, so if we okay, the consider the following language. Um, okay, let's say there is an x1 for all um, x2, phi of say x1, x2, and so on up to xn. Uh, so if this is satisfiable, then okay, is true. So I mean, so in case of the SAT, there was only this there exists quantification for all of them, right? There exists x1, x2, and so on up to xn.
Yes.
Okay, but I can come up with variations of the problem, and I can insist that no, I don't want there exists x2, I want for every choice of x2, I want this to be true. And whenever I don't say anything, I meant.
Yes, this is like a two-player game kind of a thing.
Right. Yeah. So this problem is of this nature. It has this, sorry, sigma 2p. Um, I mean, this problem is in sigma 2p, right? Because I can verify this. Given assignments, I can verify this in polytime. And then you have this, um, yeah,
Yes,
you have,
yes,
okay. Similarly, I can just go on changing this instead of making, I can, instead of this, if I define it like this, for all x1, there exists x2, for all x3, there exists x4, and so on. So, whatever, I can keep on changing, like slightly changing the definitions, and uh, I can get languages that belong to the desired class in the polynomial hierarchy.
yes, yes.
Okay, so yeah, so this is just a, um, just one example of, uh, I mean, languages in each of these classes, but there are also natural problems, more like the ones that you saw that fall into these classes. I mean, I've seen people study up to the sigma 3p hierarchy, but I'm not aware of something above that. But I mean, all of these are very well studied things, coming up with algorithms for these problems in these classes, or coming up with consequences. That's something that's an active uh, branch of exploration. Okay, so okay, I think I'll talk about reductions now. Is this is there any question about this?
No, it's clear. Yeah, thanks.
Okay. Hmm. Okay. So I'll talk a little bit about reductions, and maybe we'll do a couple of non-trivial examples. Okay. So we'll go back to this diagram where we had our first NP complete language, which was CircuitSat. Okay, and from CircuitSat you can, I think, yeah, you might have done this in class. From CircuitSat you 3CNF SAT or simply 3SAT. You show a reduction from CircuitSat to 3SAT, from, or in fact CircuitSat to SAT, from SAT to 3SAT. Once you have 3SAT, you might have done, I think, yeah, this is something that we didn't do in the class, but 3SAT to vertex cover to independent set. Independent, of course, these are bidirectional. So from here, you can go to click and several others. 3 coloring, and yeah, and a lot of examples that fall into this. But um, what we'll try to look into for now is, I think you might have done these reductions, right?
Yes, yes, yes.
Okay. So what we'll look into is, for now we'll just look into the first two. So the Cook-Levin theorem gives you a reduction to the circuit SAT problem. That is, yeah. I mean, the circuit SAT is just that you've been given a circuit, and yeah, and you will say yes if the circuit has a satisfactory assignment and no otherwise. So what we want to show is, okay, so and when I say SAT, it's a what we mean is that this is a formula, this is a circuit, and the difference between circuits and formulas is that, in formulas, the fan out of every gate is at most one, that is reusing of so okay, so if I draw it like this, there may be some inputs that are shared. This is a formula because if you look at every gate in the circuit, it only goes to, uh, it only has one wire that is coming out of it. So if you think of it as a directed graph, there's only one outgoing edge, at most one outgoing edge. But if I draw it like this, let's say the output of this AND gate feeds here, output of this OR gate feeds here, then I'm violating the property that there is only one outgoing wire. So this is a circuit where, so formulas are just circuits where each gate has at most one um, output wire, or outgoing edge or wire, whatever you want. Okay, so so this is, I mean, you can even directly show that circuit SAT reduces to 3 sets. So what okay. So what we'll do is, we'll try to relax the problem. So we know that circuit SAT is one of the hardest problems that you have in NP. It's a representative of the NP complete class. So what about relaxing the problem? Let's say I'm um, I'm let's say telling you that the depth of the I'm giving you a circuit with depth 1, and the answer is same, say yes if it is satisfiable, um, and no otherwise. So what do I mean by the depth? So okay, so if you think of the layers of the circuit, so from input, let's say these are the gates that directly take inputs. These are your layer 1 circuits, or depth 1. This is at depth 1. Then you can think of uh, gates above it which take outputs from everything below it. So these are the levels of your circuit, and if there are, let's say, d many levels, then I'll say that the depth of the circuit is d. Okay, so what does a depth 1 circuit look like? There's only one output gate, and there are inputs feeding into it, or whichever gate you want to think of. This is what a depth 1 circuit looks like. A depth 2 circuit would look like, would look something like this. Okay, so for now, let's say we are restricting ourselves to depth 1 circuits. Then, is the problem still NP hard, or can you come up with easy algorithms?
So then it would be easy because if like say this is n thing, if I find even one input value as 0, so the entire thing is going to be 0. But still I have to explore 2 raised to the power n number of the possibilities. So I mean So then this is not easier probably, and this is of the same hardness as the original problem is.
Okay, so okay, so let us try to um, yeah, let's try to see when the, let's say I'm fixing the top gate to be OR. Okay, and I have x1 to xn these many inputs. So I want to check whether this, okay, I mean these could be literals, right? I mean, I'm not writing it that way at the moment, but yeah, these are literals, not necessarily just positive variables. So I want to check whether this OR gate ever outputs a 1.
Oh, if it is a case of ever output, then yeah. So then I'll have to check that if one of the literal is a one, then the entire thing will become one. And so, how many such assignments would be there in which we do not find anyone? So that would be comprising of all zeros, say, the values of these literals. But that would be just one possibility. So there are the higher chances that I would be able to, I mean, get this thing in the polynomial time.
Hmm.
Uh,
But
yes,
but you are solving a harder problem here, because the question is just asking whether it is satisfiable. So whether there is some assignment that will make the circuit evaluate to 1.
yes, yes. So then, but then this is a simple problem, isn't it? This is simpler
Exactly.
compared to the traditional satisfiability problem.
Exactly.
Yes, because now I need not to explore all the 2 raised to the power n number of the possibilities.
Yes.
Right. Yes.
Yes. In fact, in this particular case, it's always true, because for an OR gate to be true, you just need one of the inputs feeding it to be true.
Right.
So that I can always do. So I'll just pick one variable. So x1 is, I'll make that true and give arbitrary assignments to any of them. The formula will always be true. Now let's say it is AND. It is AND of some literals. Then how do you check whether it is satisfiable?
But again, the hardness would remain the same because now I'll have to ensure that I will only be giving an input wherein all the values are 1. Then only this entire thing will come out to be 1.
Exactly.
And there would be only one such possibility. So if you out of the 2 raised to the power n number of the possibilities, there would be only one possibility wherein the values of all the literals is a 1.
Right. Or there may be a possibility, or there may not be a possibility. Can you come
Right,
up?
right.
Huh. So when is it that an AND gate or an AND circuit does not have a satisfying assignment?
So if any value came out to be 0, so then this won't be having a satisfying assignment. If the value of any literal came out to be 0, then this is not. I mean, the output won't be equals to 1.
So how do I check that? So uh, I mean, when let's say xi feeds into the AND gate, then it has to be true. It, otherwise the assignment will not be true. If x2 bar feeds into it, then x2 has to be false, so that, because we want all of them to be true. So I can keep on doing that and ultimately get a satisfying assignment. But at some point, let's say I encounter an x1 bar, then I'm running into a problem, because x1 was already true and now I want x1 bar to be true. That means x1 to be false, which cannot happen simultaneously. So the only problem that happened in this algorithm of finding a satisfiable assignment is when I come up with a contradictory requirement that xi is also feeding into that gate, and at the same time xi bar is also feeding into that gate.
Yes,
Yeah.
yes.
So yeah. So what is the algorithm eventually? So if you want to check whether an AND circuit has a satisfiable assignment or not, what is it that you would do? to the input.
Uh, oh, I see. Uh, so the thing is that okay, satisfying assignment or not. So still, I would go for the solution which I initially proposed. So I just need to find a value and which is not one. If all the values are 1, then this will result into a satisfying assignment. And even if the values of one of the literal came out is a 0, so then this would be non-satisfying assignment.
Right. So, yeah. So, what you'll do is or in other words, you'll simply check if there is an xi such that xi and negation xi both feed into the AND gate. If so, then output no, it is not satisfiable, and otherwise output yes, because I can come up with a satisfying assignment. So yeah, so what this shows is that even though the circuit SAT problem, uh, that I mean, even though the problem is NP complete, if I study certain restrictions of it, it so happens that the problem becomes easy. So what we know is that for depth 1, circuit SAT problem is in P. Okay, so then let's ask the next question. Instead of depth 1, let's say I make it a depth 2. Then what happens? So input to me is a circuit C which has depth 2, and output yes, again if satisfiable, and no otherwise. So let's say, what does a depth 2 circuit look like? So it's either an OR of ANDs or an AND of ORs. Because why is that? Because something like this, let me just show an example. So something like this can always be converted into this, right?
Um, yes, possible.
Yeah, so without loss of and similarly, if even if there were ants at the second level here, I can always club them into the top gate and get into this form. So always, so this OR of ants is something that we call as disjunctive normal form, and the AND of OR structure, this is what we call the conjunctive normal form. So let's say these are the only two kinds of circuits that are the depth 2 circuits that are possible. So let's say it's a DNF formula. Let's say we are in this particular case, and now you want to check whether a DNF that I've given you is satisfiable or not. So what is your I mean, can you come up with an algorithm, or do we hit into a block?
So since I need to execute the previous algorithm,
Hmm.
that the depth one algorithm for this AND circuit multiple number of the times.
Hmm.
Like say in this case, I need to execute that algorithm 3 times. And after the execution of the 3 times, then I can use the OR algorithm which you gave once. So effectively, the algorithm which you explained in the previous slide need to
Hmm.
be executed 4 times.
Exactly, which is polynomial times, because the input to us is a circuit. So yeah, so we are only running the size of circuit many times. So what we know that this OR gate will output 1 if any of these three output a 1. So essentially what we are going to do is, I'll call this C1, C2, C3. So just check if any of the are satisfiable, and we know how to do this in polynomial time. So each of this can be done in polytime, and there are only k many of them. So we are still running in polynomial in terms of time. So if any of them is satisfiable, then we will say yes. Okay, but what about the other case? Let's say the input is a CNF. Then you'll do the same thing, right? You'll just check if all of them are satisfiable.
Yes, yes.
Okay, so okay, so check if okay, but okay, I mean um okay, one catch here is that we are independently checking here, right? I'm just checking whether C1 is satisfiable with respect to these inputs, C2 is satisfiable with respect to these, and so on, right? It may happen that okay, C1 is satisfiable when the inputs are the inputs are 0 1 0 1, and C2 is okay. I'll sort of write it nicely. So let's say C1 depends on x1 x2 x3, and C2 takes x2 x3 x4 x5. So let's say C1 is satisfiable when the only when the inputs are 1 0 1 respectively, and let's say C2 is satisfiable when the inputs are 0 0 1 0. Okay, so C1 is independently satisfiable, C2 is independently satisfiable.
So quite possible that there could be a clash. Yes.
Exactly. Yeah.
Yeah.
So that clash does not affect us in the case of DNF. Why is that?
Uh, because this is end thing, and end thing would mean that things have to be all ones, all ones. However, in the case of the CNF, the conflict, I mean, we'll have to pay more for every conflict,
Hmm.
because then, yeah.
Yeah, because for the DNF you only want one of them to be satisfiable. Even if one of these is satisfiable, we are done. We don't care whether the others are simultaneously uh, satisfiable or not. But in the case of AND, you want all of them to be simultaneously satisfiable. Therefore, the input assignment here has to be consistent.
Yes.
Okay, so then what can we say is the CNF problem with the depth 2, of course, is it hard as hard as the previous one, or is it, I mean, or maybe there is some other algorithm that we couldn't think of at the moment.
So, but then since DNF and CNF are interchangeable, so I mean the hardness of the problem should remain the same. But then from this diagram, it appears that as if the CNF is harder compared to the DNF thing. However, I mean, so it seems that as if, but the point here is that, but the point here is that, yeah. So I mean, but the point here is that we are having or gates at the second level.
Hmm.
So even if one value is true, the entire thing will came out to be true.
Hmm.
So even if there are the conflicting values,
Hmm.
will it affect the final value or not? So even if there are the conflicting values,
Hmm.
so the entire thing will came out to be a zero. But then this is the nature of the problem, and why should we worry about it? I think that both the problems are of the same hardness.
Okay, so let's say even okay, so let's say that you are um, sort of okay. Mm, yeah. So we are saying that okay, here you have an OR gate. So you just need one input to be true among all of them. You don't need all of them to be true. But how there are so many choices that we have to make at this point. So which is the correct choice? So let's say I arbitrarily choose the first one, and I want to make it true, and the rest of them I leave free because I'm going to choose them later on as per my convenience. So let's say the first one, whichever was feeding, I made it a 1. And at some point, let's say this gate was using uh, this variable as a negation. So that means I'll have to look at the other inputs and have to make sure that one of the other two is a true value. So let's say I'll arbitrarily again choose something and I'll make it a 1 because this guy was feeding in as a 0. But then that same thing could keep happening over and over again. So the point is, how do I know what choice to make? Because the choices I made, so let's say with this particular choice of input as 1 and continuing the algorithm, maybe that does not give me uh, eventually it does not give me a satisfiable assignment because there were so many choices that I made. There could be some choice that leads to it. So how do I know which is the correct choice?
Yes. So the thing is that the leftmost input
Hmm.
uh, for this OR
Hmm.
should be marked as 1. I mean the
Okay.
left extreme. I mark
Okay.
this as the 1 and the remaining inputs would be don't care.
Okay.
Don't care for this OR thing. And so I keep on scanning and then for the second OR, again I mark its leftmost as 1
Hmm.
and then mark the other as the don't care thing.
Hmm.
Now there could be a conflict in the
Hmm.
leftmost one and the so then yeah then I instead of the one if there is a conflict with the value one
Hmm.
then I'll mark the second thing as one and but then
Hmm.
I do not know whether this will actually work or not. No, not
Exactly.
sure.
Right. So it could be exponentially many choices again at the end.
Yes, yes.
Right. So it is not clear. I mean, if we think of the obvious approaches, it's not clear at the moment whether CNF is easy or not. CNF as in depth to CNF. Okay. So, okay. Sorry, I shouldn't even. Sorry, I'm sorry for the terminology. I shouldn't say depth to CNF. When I say CNF, I mean, by definition, it's a depth to circuit because it's an AND of ORs. Okay, so at the moment, it looks like DNF is easy. That is what we concluded. So, DNF satisfiability checking is easy, and CNF SAT is not clear at the moment. In fact, it turns out that this is hard because why is that? I mean, because any circuit that I give you, like we saw earlier, can be written as a CNF or a DNF, right? So, I mean, okay. What I'm trying to say is that the SAT instance that we've been solving so far, right? The fee that is given to us is an OR of, sorry, an AND of ORs. This is nothing but a CNF, right? So we have, I mean, just take these gates, club them together here, and yeah, and yeah, and you have this clauses here. And we know that SAT is NP complete.
Yes.
So that sort of tells us that this should be hard. The CNF SAT.
So CNF satisfiability is so CNF is conjunctive. Conjunctive would mean what? Conjunctive C and then D. So would be the end of the ORs, right? So if this is the end of the ORs, so even if one becomes, uh, yeah. So CNF satisfiability is hard. Is hard.
Exactly. So that's what we used. you used in the class for showing that vertex cover is hard, independent set is hard, and so on. You had already assumed that 3 sat is hard. 3 sat meaning 3 CNF sat. And okay, so what is the 3 here? It just means that the number of uh, yeah, the number of elements in the clause here. So each of these is a clause, that is these triangles that we had drawn earlier, these are clauses. Okay, and there are 3 literals here, therefore we call it a 3 CNF sat. That is the fan in of each of the gates here is 3. Okay, so that is 3 CNF sat for us. Okay, so you can think of yeah, so okay, I mean, is the definition of 3 CNF sat clear?
Yes, it is clear to me, but then I don't exactly remember, but then DNF and the CNF used to be equivalent to each other. Is this not the case?
Yes, so okay, good. So you know that if I give you a DNF, you can convert it into a CNF, right? So I'll okay, whatever is the other input here. How do I convert this into a CNF? If think of this as phi1, phi2, phi3. So the DNF is nothing but phi1 or phi2 or phi3. And I want to convert these into ANDs, right? So what we do is we do the De Morgan application. So you do a negation of this formula, which is
Yes.
phi1 complement and phi2 complement and phi3 complement. So now uh, I mean, phi here had an OR gate, right? And you do the same thing again. So you can convert this OR into, I mean, with this one application, you have gotten this OR into and you can do this, push down those negations and get this into ORs. Okay, but yeah, so this part is in the CNF form now. Okay, but notice that this has changed the um, definition of the problem itself. So you want, when you say you want this to be satisfiable, this is exactly not satisfiable.
Yes. Now I understood the point.
That
Yeah.
is the tautology sort. Okay,
Tautology
yeah,
thing. Yeah. Co-NP thing.
exactly. So yeah, so you've kind of gotten the complement of that formula in the CNF form. So yeah, so
Yes. This is a very interesting and very crucial point. Yeah, I understood this thing.
okay, good. So yeah, so we are at the conclusion that this is easy, this is hard. So what we'll do again, so why did we get here? Because we said that okay, circuit sat is hard. Let us look at the easy versions of it. Depth 1 was easy, we looked at depth 2. Depth 2 may this DNF case was easy, but the CNF thing was hard. So natural thing to do, I mean, this is uh, this is the kind of thing that people do in research all the time. You know, something is hard. First thing to do is always tone it down, look at the restrictions, and understand where the hardness exactly begins. So that's what we'll do again. So we know that CNF SAT is hard. So what we'll do is we will further look at some properties of it. So let's say this is an AND of ORs, and now I'll define um, yeah, the arity of this OR gate. Okay, um, okay. So we'll look at the arity of this OR gate. Okay, it can be, which is nothing but the number of inputs that are feeding into it, and for the sake of uh, for the sake of ease, assume that these are all equal. If not, you can always add dummy inputs. Just look at the maximum arity here, and you can always make the rest of them take those many inputs by just feeding in some dumb input. So for the sake of consistency, let's assume that the arity of all of them is same. So let's say, so I'll call this version a KSAT or KCNFSAT. What? Okay. What do I mean by that? The fan-in of the orchid there is K. Natural question: if K is 1, what will happen to the hardness of the problem?
So so yes, so if k is 1, then the problem is pretty easy. I mean, just evaluating an expression, that's it.
Exactly. So it's just an AND of, because that OR is essentially redundant. There's only one input feeding into it. I'll remove that OR kit and directly feed that input. So yeah, so it's the first case that we saw, the depth one case, and we know this can be done in polynomial time. So let's say k is equal to 2.
So if k is equal to 2, then also it should be easy, because if I fix the value of the one variable, probably the value of the other variable will also get fixed. I don't know. Maybe it would be easy.
It it could be easy, but um, yeah, I mean, we want something provably easy, because we'll run into the same issue here that we had earlier, right? So I have a choice of choosing which of the two inputs to fix to 1, and once I make that choice, you sort of branch out every time. For this guy you make a choice, for the next one I might have to make a choice again. So each time there is a split that is happening, and these are sort of exponentially many choices that we're making, I mean possibilities that are there. So um so if I mean so it's not obvious at the moment why this is easy. Okay, so this is called 2SAT, and it turns out that this is in P. Okay, but we'll look into it after a while. Okay, if there's time we'll look into it now. It's a very interesting and a very beautiful proof that uses uh, the idea of graphs. Okay, so it's converting a circuit problem into a graph problem, which you might have done in the class, I'm not sure, but most of the reductions that you have seen, the vertex cover, independent set, click, and so on, those are the kind of reductions that take the same kind of object and reduce it into the same kind of object, which is kind of easy. But once I give you two different objects coming up from a circuit to a graph, or looking for some other property, that's more involving and interesting as well. So we'll look into this in a while. Before that, before getting there, let's say when k is 3, that is when you have your 3SAT problem, which you have done, I mean which you have done in the class, right? So we know that 3SAT is hard. How do we know that? We'll actually we can actually show that circuit SAT reduces to 3SAT in polytime. So this is a uh, very nice reduction, which manipulates the circuit in a certain way. You can, I'm not sure if this was done in the class, but if you're interested, you can look into this. What I want to show now is the following. Let's say, um, okay, so we said that 1 is easy, 1 is easy, 2 is easy, which we haven't proved at the moment, okay, and 3 is hard. That means uh, there is a certain parameter at which the hardness sits. Beyond this 3, what happens is 4 SAT is also hard, 5 SAT is also hard, and so on. Everything after that is hard. So let's say I want to prove this part. I want to show that k SAT in general reduces to 3 SAT, where k is greater than 3. This is a polytime many-one reduction. So this is what we want to show. So how do we go about it?
So, but then in the Boolean algebra, even if I mean any Boolean algebra, uh, the difficult one, I mean, if it is not two set, then it can be represented as three set, isn't it? No,
Uh,
CNF. No, no. Every Boolean formula can be written into the CNF form. CNF set. That is true,
that is true.
right? And now we want to. So the meaning of the three set would be that there are at most three literals in every clause, or the exact three number of the literals in every clause.
Yeah, we can work with either definition, because if there are less than three literals feeding into it, like we said, I can add some dummy literal and
Okay,
make it
okay.
exactly three. So, hmm. So maybe let's say let's work with a specific example. Let's say K is 5, and see whether that same strategy generalizes to any general K. Okay. So let's say I want to show this. What does every clause look like? It's some A1 or A2, or maybe I should call it LI L11, and so on. Okay. So what I want to do is that I want to break this into three CNF formats. So maybe something that has, and so on. So each of these I want to break it like this. And this is the original formula fee that we had, which was in the 5 CNF SAT format. And let's say this is the new formula that I get after some pre-process, I mean after some processing. So what we want in order for this to be a valid reduction, is that phi is satisfiable if and only if phi bar is satisfiable. And this phi that we have is in the 5 SAT format, and this phi prime that we have is in the 3 SAT format. So what is a very natural um, thing that you can come up with, even if not the exact formula? What should be the intuition or the idea behind this um,
Yes,
reduction?
yeah. So whenever every clause in phi is true, then since every clause now has to be split into two clauses in
Hmm.
phi prime,
Hmm.
and one would be having three, the other one would be having two. Uh, like say, so three and then two. Probably this is slightly incorrect here, isn't it? Because there would be three and two. Okay. So, how to ensure that whenever
Hmm.
a clause in phi is true, then the two clauses in phi prime are also true, and both have to be true simultaneously because this is now an end. So I have to split this 5 into two quantities. So, but then every clause in phi would be true even if one value is true.
Hmm.
So that would mean that uh, yes, but I yeah.
So that would mean you sort of need some new variables to make sure that whenever either, I mean, you're breaking it into some parts, right? So these five are going to be broken into several parts. We don't know how many at the moment. We just want to make sure that whenever either of them is true, we should be able to produce a satisfiable assignment here. So that
Yes.
means I'm sort of in need of some extra dummy variables which will take care of that fact. So let's say I'm going to break it like this. the dummy ones I'll call, let's say, D1, and I'll read. So why are we doing this? Because what I want to intuitively capture is that, let's say this part was true, okay, then it will make this clause true. And what I want now is, no matter what lies ahead, I want to make them true. I want to have a way of making them true, even though these factors, these subsets may not contribute to a value of true. So this dummy variable will take care of the fact that they are going to be always set to true whenever, let's say, this is true. So um, yeah, I'll just yeah. So let's say this part evaluated to true. Then what I'll do is I'll set my dummy variable to false, so that this guy becomes true, and no matter what lies ahead, it will evaluate the clause to true. Okay, so I'll write the next variable here and d2 and keep on doing this. So sorry, the last one would be simply this. So is the intuition clear why we got the dummy variables here?
Actually, this is not that clear. Why so? Because even if L11 is a 1, then this entire clause in original 5 would be a 1.
Hmm.
And the same thing is happening here also.
Hmm.
But then here you made this thing mandatory that L12 should also be a true. Why so?
No, no, no. We just said that L11 or L12 is true. Then we
Yes,
will
yes,
set
yes,
this.
yes. Now it's correct. Yeah.
Hmm. So, I mean, same thing can happen, I mean, anywhere, right? Even if, let's say, the clause was true, because L13 was true, then how will you show me that there is still an assignment here that makes it true?
So, like, say if L11 and L12 is, I mean,
False.
false. So, if it is false, both are false.
Huh, both are false. So,
False. So
D1
then
and.
we have taken say D1 as true.
Hmm.
So
So,
if D1 is true, the complement of D1 would be a false. Then
false.
so then I mean one out of these things should be a true.
But L13 was true.
Yes.
So I can safely make this false,
Yes.
and therefore this becomes true, and
Yes. Yes.
therefore
Yes.
all of,
Yes.
sorry,
Yes.
yeah. So this is just one direction of the proof, that if phi were satisfiable, then for every clause, we know that the corresponding surgery that we did is also going to be satisfiable, and therefore the conjunction is going to be true.
Yes.
Okay,
Yes.
so we want to now argue the other direction, that let's say V is not satisfiable. That means, say, okay, I mean, either you want to do the contraposition way or the direct way. It's up to you. I mean, hmm,
So yes. Yes. And even this is clear from here. Here also, like say if this is false.
hmm,
So then all the this can happen if all the literals are I mean having false values.
hmm.
So if
Then,
that is the case, the only thing would be that I make the D1 as true. But if I make the D1 as true, so then the D1 complement will become false. And if it
so,
becomes false, then I have no other option except making the D2 as true.
hmm,
If I make that as true and so then this will become false. But then one thing is getting, I mean, it may result into a true value. Yeah,
But you know that, okay, so sorry, I'm just looking for the tool. Huh. You know that the conjunction is false, therefore there is some clause which is um, false.
yes,
So without loss of generality, let's say it is this clause. Okay, then that means that all of the li's here are false.
correct.
So this is false, and also this is false. So I just get this. Okay, this is false, this is false, and also this is false. So what we are saying is that for this to be true, d1 must be true. That forces this to be false. So you have no other option. It sort of keeps forcing like a chain that d2 must be true, and so on. But at the end, you will end up in a situation where this guy is also forced to be false. But
Right,
yeah, but the last part in that whole chain, this the last half is already false because of the assumption that we made, and the first part is forced to be false, therefore this clause becomes false.
right. It's true. I understood.
Okay, so I'm not writing it formally right now, but yeah, I just wanted to show the idea. So this was the case for 5 sat, right? In general, I give you a k sat. Then how do we break it?
So then we will break it like, say, we will make a triplet, I mean triples of uh, the literals. Like, say,
Okay.
if we have been given k number of the Boolean literals, then
Hmm.
how many triples are possible?
Hmm.
So I would be selecting two literals in the first triple,
Hmm.
and and then a dummy.
Hmm.
And then in the second triple, I would be selecting just one literal from
Hmm.
here and then two dummies. And then I'll construct this in this way so that eventually the final Boolean expression
Hmm.
uh, will result into a false value if that is the second case.
So you'll need k minus 3 many dummies.
Yes, yes.
Okay, and okay, and one thing to argue here is that this reduction is, of course, polynomial time reduction, and because the blow up that is happening here is polytime, right? So poly sized only. So for a k length literal, we are only adding k minus 3 many more dummies, and this surgery is very locally doable. So we are just looking at the literal and splitting it like this. So this can be done in polynomial time. Okay. So one thing to note here is that, okay, so that means I can convert my 6 sat instance in, I mean, um, okay, any k greater than 3 sat instance into 3 sat. The question is, why can't we do this for 2 sat? Um,
So, but then certainly two set is an element of P. So, yeah, and I do not remember its formal proof, but then probably it could be something like, if I fix, so if two set is given, so if there are only two literals, and if I follow this strategy,
hmm,
so and because if I fix the value of the one variable,
hmm,
so the value of the other variable will get fixed automatically, isn't it? That could
yeah.
be a false
Hmm.
value. But yeah, that I do not have any concrete statement on this, but
Hmm.
except that this is a known result that 2 set is the element of P.
Hmm. Okay, so I'll just in the next maybe 5-10 minutes, but I'll just quickly give the intuition of why it is in P. Maybe we may not be able to write it formally, but the idea is very very interesting. So okay, so what does the instance look like? It is L11 or L12 and L21 or L22 and so on. Okay, so what I'm going to do is I'm going to write this as an implication. So what do we mean by that? When I say A implies B, we know that this is logically equivalent to A or B, right?
Yes, yes.
So if I want to write L11 or L12 as a logical implication, how do I write that?
So that would be the negation of L1 implies L12.
L12, or equivalently, the negation of L12 implies L11.
Yes, this is also true. This is also true.
Right. So why am I writing it like this? Because
No,
it
no, no. Probably this is not true because the it would mean what? The negation of L11 or L1. Yes, this is true. Yeah, right.
this is a contraposition of the previous one, right? A
Yes,
implies B, then B bar implies A.
yes,
B bar implies A bar, sorry.
yes, yes.
Okay. So why am I writing it like this? Because when I write as an implication, what do we mean? That when I say A implies B, I mean that if A is true, then B better be true for the entire uh, proposition to be true, right? So it's sort of showing an implication of, like, it's forcing the truth values. So when I let's say, yeah, so when I say x1 or x2 bar and x3 or x5 bar, let's say x5 and x2 or x3 bar, let's say, and there are several others. So we'll do the same thing that we said just now, that I think of this as a graph where the vertices are x1 bar, um, okay, x2 bar and so on. So if there are n variables, there are 2n many vertices here. And what we said just now is that I can write this thing as x1 bar implies x2 bar, as well as I can write this as x2 implies x1. Okay, so I'll just draw this implication in term as a graph. So we'll call it an implication graph. So when I say x1 bar implies x2, I look at x1 bar and draw an arrow like this. Equivalently, we can write it as x2 implies x1. So I'll draw an arrow from x2. Sorry, I think I did it incorrectly. Yeah, it is from x1 bar to x2 bar and from x2 to x1. Okay, and keep on doing this. So for every clause, you get two arrows. So when I have x3 or x5, I'll draw from x3 bar to x5. Sorry. Okay, I'll draw from x3 bar to x5 and x5 bar to x3. And similarly, we keep on doing this. So ultimately, you'll get a directed graph. Okay, so can you see some property about this graph? Okay. Um, I'll call this graph G, and clearly the reduction was polynomial time. So this was the whole reduction from a formula phi. We came up with a graph G, and what we want to argue is that phi is satisfiable if and only if there is some property that I'm looking at. So phi is satisfiable if and only if there is some property that I'm looking at which is satisfied by, or let's say G satisfies this particular property. I'll call it property X for now. So can you identify uh, some property in this graph that would make the formula true or make the formula false?
So for every clause we are drawing two edges,
Hmm.
and if if a clause and to get this phi satisfiable, every clause should return a true value. So then I should be able to move from x1 to, like, say, x1 bar to
Hmm.
x2 bar,
Hmm.
and but I should move, and both would be disjoint. Yes, I mean both the arrows would be disjoint. So the thing would be that I start traversing from the x1 complement, and the traversal should be like that. I mean, so it is indirectly, it is asking that as if I start my journey from
Hmm.
x1 complement,
Hmm.
and would I be able to reach to x3 or not? That kind of thing.
Huh. Right. Good. So yeah, it's very close. So what the observation that we made earlier was that what this arrow intuitively says in terms of the formula is that if I make L11 bar as true, then L21 has to be true in order for the formula to be true. So it's kind of conducting the truth. So when I say that x1 bar to x2 bar is an arrow, if x1 bar is true, x2 bar better be true. Now from x2 bar there may be some arrow due to some other clause here. So what that means is if x2 bar is true, then x3 bar better be true, and so on. So if I keep on going like this, and I, let's say, ever uh, reach x3 bar, okay, or okay, maybe even simpler, let's say I ever reach x1, then what does that mean?
So I mean, in this hierarchy, in this I mean, in these stages of assigning the truth values, it would mean that x2 complement is true, but then x1 is not true. I mean, x2 complement is true, x3 is true, but since we are unable to reach to x1, so x1 can never be a true value.
mm, okay, I mean, in this case we are able to reach x1, no?
Yes,
So
yes.
what does that mean that we are able to reach x1 means? um,
So, but then here we are able to reach to x1, but then we have taken both the edges, both the red edges into the count, and the both the red edges are because of the first clause only.
okay.
Uh, yes.
Okay.
So this would mean that whenever x1 complement is true, so but then this leads to a contradiction as well. Uh,
Exactly.
yes.
Yeah. So, yeah, that's the point. So, what happened is that because you were conducting the truth value, just following the edges, you eventually ended up in a situation where x1 is true, but you already assigned x1 bar to be true. So, both of them cannot be true at the same time. In fact, that contradiction happened much earlier here, that x2 bar is true, and you are also saying that x2 should be true. So, what this what we want to say is that the property x that we are looking at is the reachability property. So I mean, I don't know, have you heard of the reachability problem in graphs?
Uh, yes, reachability. Like say, we can conduct the DFS kind of thing to
Yeah,
know the
DFS would be
reachable.
just
Yeah.
one algorithm to do it, but the problem in general just says given a graph G and a source and a target vertex T, output yes if there is a path from S to T. So,
Yes,
or you
and
can just
this is
call it a
yeah,
path. Yeah.
this is the element of NL complexity class.
Yes.
Yeah.
Okay. So this is the property that we are looking at. That is, we are saying that if there is an I such that uh, there is a path from xi to xi bar in the, I'll call this implication graph G, then we observe that then phi is not satisfiable, because what that meant is that yeah, if let's say mm, huh, okay, we'll maybe take a look at the first thing here. So x1 or x2 bar, for this to be true, uh, if x1 bar is true, then x2 bar has to be true. That means, in other words, if x1 were false, then it has to be that x2 bar has to be true. So hmm, okay, and we kept on following the directions, right? So it's basically tracing um, the values that are forced whenever we choose an assignment. And for the other case, when x1 or let's say x2 bar is true, that is captured by the other arrows. So all the possibilities are taken care of. And yeah, and whenever we come up with a situation like this where uh, there are inconsistent I mean there's a contradictory assignment, then um, yeah, then we know that the fee is not set. So I mean, I haven't written it properly, but I'm just trying to give you an intuition. And similarly, we have to argue in the other direction as well, that if fee is indeed satisfiable, then for all I, there is no, there does not exist an xi to xi bar path. So these are the two things that one needs to formally argue. But the reason why I wanted to, yeah, just talk about this is because it's a nice I mean, it's a nice idea where you have formulas at one hand or circuits at one hand, and you convert it into a graph instance where you're looking for some interesting, I mean, some simple property. So um, yeah, I think I'll stop with that for now. But yeah, if there are any questions, then do ask.
Yes, this is clear. Yeah, by and large, this is clear. But I'll have to go through this proof again. But then this proof is really very interesting. Yeah, thanks.
Okay, so okay, I'll just stop the recording and talk about the next class.